What about triple on?
Go ahead, ask the question.
Yeah, what about triple angular?
Triple angle and double angle, we're getting it from the compound angle. I will show you how to do one, and you could get quadruple angle, quintuple angle, whatever angle you want. Right? But it's just a big simplification process you'll have to do. Right? Big. All right. So let me dive into radian measure. Now, just as in good Lord, when we measure in distances, right? How much units we have to measure distances in?
Okay, got it. Well, centimeters, meters, kilometers, that kind of thing.
Quite a few. Yeah.
Yeah.
The hectares, kilo, mega, gigameters, that whole thing, right? All the prefixes. In radian, in angular measure, there are two we focus on. One we have been learning from since we born, degrees, degrees Celsius, or degrees Fahrenheit. Yeah? Nice temperature, boy.
I know, yeah,
Angle.
I do physics as well.
Right? So another unit that we measure angles in shapes is radians. Now, it might be a little unconventional in the beginning because we will be using the concept of pi. And we know pi is 22/7 or 3.14. And pi represents the ratio of the circumference of a circle to its diameter. We don't know pi to be an angle. So in radian measure, there is a relationship, just like there's a relationship between centimeters to meters, there's a relationship between radians to degrees. So pi radians is 180 degrees. And this is the convention that we need to build the foundation on. If pi radians is 180 degrees, I want you to be comfortable doing two things. 1 radian is 180 degrees over pi. Do work out the number. Don't punch it in a calculator. Do work out the number. And 1 degree is equal to pi over 180 radians. All right, these are the two conventions I want you to be very comfortable with. So for example, what is pi on 4 radians? Well, pi on 4 radians is equal to 180 degrees over pi multiplied by pi on 4. This will happen every single time. The pi's will cancel out and I'll get 45 degrees. So, a note I would like you to mentally take here. Whenever we are expressing an angle in terms of radians, it always has a pi attached to it. 2 pi, 14 pi, 14 pi on 7, 14 pi on 12, 6 pi on 3, 7 pi on 2. Right? You will always have a pi in your radian measure. The pi will always be on the numerator. Very rare you'll have pi being on the denominator when we are expressing an angle in terms of radians. Degrees is always in degrees. It has no pi in degrees. All right? So the first example was a conversion from radians to degrees. And 90 degrees could be pi over 180 multiplied by 90, bam, bam, 2. We get pi on 2 radians. So radians is always in terms of pi. It's in terms of pi. Do not substitute pi to be 22/7. Don't substitute pi to be 3.14 unless specified, unless you're performing more calculations involving radians. All right. Some good numbers to know, very, very good numbers to know. Pi on 4, pi on 6, pi on 3, pi on 2, 2 pi. Pi on 4 is 45 degrees. Pi on 6 is 30 degrees. Pi on 3 is 60 degrees. Pi on 2 is 90 degrees. And 2 pi is 360 degrees. Good numbers to know off the top of your head, right? In terms of radians. Now, how are we going to incorporate radian measure in a calculation? And when do we use radians? Let's take an example here. And I'll probably take an example from the same exam that we had. All right, we'll use this one here, right? And we will incorporate the double angle and the triple angle formula in this solution. All right. It is one of the more difficult questions that you can get in trigonometry. But if we start with the difficult stuff and then work our way down, you'll see how easy things are. Right. So unconventionally, I'm going to start with a difficult question and work our way down, opposed to starting easy questions and working our way up. So I'm going to bring this across. Now, the first part says the proof. We had to prove something, right? Prove that cosine 3x is 4 cos cube x minus 3 cosine x. Okay, no problem at all. Now, in the proof, we'll have to use the double angle and the compound angle formulas. All right. So let me start. Cosine 3x is equal to cosine of 2x plus x. Can you agree on that?
Mm-hmm.
Good. If I recall, this is of the form cosine of a plus b, where a is 2x and b is x. And that is cosine a, cosine b, minus sine a, sine b. Yeah? Cosine a, cosine b, minus sine a, sine b. So we're going to be exposed to the double angle formula now. I don't know what cosine of 2x is. I know it's cosine of x plus x. Yeah?
Yeah.
I already recall the identity, so I don't need to recall it again. This is cosine x minus sine x sine x. Cos x by cos x is cosine squared x minus sine squared x. So cosine of 2x is cos squared x minus sine squared x. Yeah. Now for cosine of 2x, we actually have a couple more identities, because one of the baby identities says that cosine squared x plus sine squared x is 1. I can get what cosine squared x is, and I can get what sine squared x is. Similarly, I have sine of 2x is equal to sine of x plus x. I sine x cos x plus cos x sine x. And this is 2 cos x sine x. Yeah?
Yeah.
Or 2 sine x cos x. Now, what is the advantage of using double angle and triple angle formulas? Or why will we want to break it down? This 3x is some representative of an angle. And we will use the double angle formulas to express a compounded angle, which is 3x, as a sum or difference of individual angles, which is x. Right? It makes life a lot easier to work with a singular angle opposed to a compound angle. So if you realize, I'm trying to break down cosine 3x in terms of cosine x's and sine of x's alone. So let me start to substitute some stuff inside of here now. Cosine 2x, as stated, is cos squared x minus sine squared x. And this was multiplied by cosine of x minus sine 2x was 2 sine x cos x. It doesn't matter which order I write it in, by sine x. Yeah? Expand, I get cosine cube x minus cosine x into sine squared x minus 2 sine squared x cosine x. And a nice little note I want to take here. Cosine x by cosine x. I've seen it happen. Students say, well, there's cosine of x squared. Because I have an x here and an x here, and x by x is x squared. I've seen cosine squared x squared. No. When we multiplying trigonometric functions by each other, the power goes in a different place. The angle is sacred. I like to call the angle very, very sacred. We don't really interfere with the angle unless we have some internal operation on the angle. So for example, I will only interfere with the angle if I have something like this. Cosine of 3 into 4x. This is the only time I'll interfere with the angle. This is cosine of 12x. Yeah? If I have 2 cosine of 3x, I'm not going to interfere with the angle because this 2 now is an external operation on the angle. It is independent from the angle. Okay? Similarly, if I have cosine x all squared, this here, the squared is an external operation on the angle. I do not interfere with the angle unless I have an operation inside with the angle itself. So where does this 2 go when we have a cosine x all squared? The power is over here on trigonometric functions for sine, cosine, and tan. So when I have cosine of x all squared, this is a 1 over here. And this becomes cosine squared x. Right? It's just a convention, a name. Cos squared x, sine squared x is nice to say. It rolls off the tongue. When we perform in a calculation with cosine squared x, we actually calculate cosine of the angle and then square it. Some calculators will actually allow you to put cosine. Well, this one wouldn't. If I press cosine and then I press the squared, it wouldn't allow me to put a squared above the cosine. Right? Some calculators will allow it, others won't. But cosine squared x is cosine of x, and then you square it. That is why for this multiplication here, the cosine x and the cosine x, the angles are independent of each other. So I do not combine those operations and have an x squared. Cosine by cosine is cosine squared. That is why we have cos squared x, same thing for the sine squared x. Okay? And sine cube, cos cube, going up the road, we perform the operations where that power, where we learn the power to be, the a. Yeah? So this is equal to cosine cube x minus. Now, my proof says I want to prove cosines in terms of cosines. Right now, I have cosine. Well, this is cosine of 3x. Right? That is cosine of 3x, which is 2x plus x. I have cosines in terms of cosines and sines. So I want to get rid of the sines. Yeah? I want to get rid of the sines. So I'll get rid of the sines here. I'll say, you know what? I remember not too long ago that sine squared x plus cos squared x is equal to 1. So I can express sine squared x in terms of cosines only. I'll make a substitution. Cos cube x minus cosine x into 1 minus cosine squared x minus 2 into 1 minus cosine squared x multiplied by cosine x. This is cosine cube x minus cosine x plus cosine cube x minus 2 cosine x plus 2 cosine cube x. Yeah? 2 by cosine is cosine, and then we multiply by each of the things in the bracket. All right? Cos cube, cos cube, cos cube. I get 4 cos cube x. Minus, minus, I get minus 3 cosine x, which is what we wanted. 4 cos cube x minus 3 cosine x. Yeah?
Yeah.
Which is what we wanted. Hence, solve for x in cos 3x plus cos 2x is equal to 0. Now, how do we know to use radian measure? Radian measure is indicated to be used when we have the domain in terms of pi. Remember, in the last set of calculations that we did, the domain here was in terms of degrees. In this question, the domain is in terms of pi. Yep. My domain is in terms of pi, which gives me the indication, use radians. So let me go. Cos 3x plus cos 2x. Let me see. This is part 2. Cos 3x plus cos 2x is equal to 0. For 0 is less than x is less than pi. I know what cos 3x is. Cos 3x is 4 cos cube x minus 3 cosine x plus, I know what cosine of 2x is. Cosine of 2x is cos squared x minus sine squared x. Yeah? Plus cos squared x minus sine squared x is equal to 0. I have different trig ratios. I want to try and get the same trig ratio, at least in the whole thing, cosines alone. So I can change the sine squared x just like we did in the proof. I'll replace the sine squared x with 1 minus cos squared x. Yeah? So I'll have 4 cos cube x minus 3. I'll put the plus cos squared x first. Minus 3 cosine x, take away 1 minus cosine squared x is equal to 0. Now I have an equation involving only cosines. I'll have 4 cosine cube x plus cosine x plus cosine squared x. Yeah?
Yep.
I get plus 2 cos squared x.
A polynomial.
Minus 3 cosine x minus 1 is equal to 0. Let me make a little convention that y is equal to cosine of x. I have 4y cubed plus 2y squared minus 3y minus 1 is equal to 0. I'll let f of y be equal to 4y cubed plus 2y squared minus 3y minus 1 is equal to 0. And we have remaining factor theorem in a Trigs question. Well, I'll go and check. F of y divided by y plus or minus something. I'm trying to get a 0. And this is where the cheating comes into play. I'm going to check when y is 1. I'll have 4 plus 2 minus 3 minus 1. I get 2. So f minus 1 is not a factor. I'll try y is equal to minus 1. I get 4 into minus 1 cubed. Minus 1 cubed is minus 1. Plus 2 by minus 1 squared is 1. Minus 3 into minus 1 minus 1. I get 0. So it's very, very safe for me to say that f of minus 1 is equal to 0. And when I get minus 1, this is supposed to be y plus 1. And we quote the remaining factor theorem. If any polynomial f of x is divided by x minus a, the remainder is f of a. If f of a is equal to 0, then x minus a is a factor of f of x. So I can say, therefore, y plus 1 is a factor of f of x. Now, you can do one of two things. You can use synthetic division, or you can use long division to figure out what the quadratic is attached to this polynomial. So let me do with long division. I'll have my y plus 1 divided by my whole big long polynomial, which was 4y cubed plus 2y squared minus 3y minus 1. I get 4y squared, and I get 4y cubed plus 4y squared, and minus them. I get 0. 2 minus 4 is minus 2y squared. Hammock these two terms and bring them down. 4y squared minus 2y. I get minus 2y squared minus 2y. Minus them again. I get 0. Minus 3 plus 2 is 5y. Hammock the minus 1 and bring it down. That is minus 3 plus 2, sorry. Minus 3 plus 2 is 1. Y minus 1. Minus y. Minus y minus.
Minus y, yeah, minus y.
So I get minus 1, and I get minus y, minus 1, minus the two of them, and I get 0. So I get f of x is equal to y plus 1 into 4y squared minus 2y minus 1. Now it's time to factorize the quadratic. So consider 4y squared minus 2y minus 1 minus 4. This cannot be factorized.
Yeah.
So we'll have to use the quadratic formula. All
1
right?
plus root 5 on 4, and then 1 minus root 5 on 4.
So f of x is that. We want to solve f of x is equal to 0. Sorry, f of y, my bad. So we're going to let y plus 1 into 4y squared minus 2y minus 1 is equal to 0. Okay, y is minus 1. Or 4y squared minus 2y minus 1 is equal to 0. Remaining factor theorem. y is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a minus 2 plus or minus 2 squared minus 4ac all over 2a. 2 plus or minus the square root of 2 to the 4. 4 plus 16 is 20. 2 plus root 20 all over 8. So y is equal to 2 plus root 20 over 8, or y is equal to 2 minus root 20 over 8. We are done yet. Remember, we let y equals the cosine x. We let y equal cosine x. So I'll give them a little recall here. Y was equal to cosine of x. So therefore, minus 1, cosine of x is equal to minus 1, or cosine of x is equal to 2 plus root 20 over 8, or cosine of x is equal to 2 minus root 20 over 8. So our three separate calculations I have to calculate for x in each case. We know that in this first case here, cosine is negative. Yeah? Cosine is negative, so solutions will lie in quadrant all school here and here. Yeah? So my principal value will be cosine inverse of the modulus of minus 1. Cosine inverse of 1 is 0. Cos inverse of 1 is 0. So my principal value is 0. Now, we're working in radians. So we need to figure out what is the convention for a quadrant in terms of radian measure. Nothing had changed. In the first quadrant, it's still the inverse of whatever, all right? So my principal value is still cosine inverse, sine inverse, tan inverse of the modulus of whatever the number was. In quadrant 2, it will be pi minus my principal value, pi plus my principal value, and 2 pi minus my principal value. All right? Very, very important. You see this degrees here in the calculator?
Yeah.
Degrees. Your calculator can be changed and has to be changed in radians if we are working in radian measure. How do we change it? Set up DRG, means degrees, radians, and gradient. So we don't want to work in degrees. We want to work in radians, which is 1. So you see it changes to radians here, right? Changes to radians. So, and this is pi, we're solving for x. So x is equal to pi minus 0, which is pi. And x is equal to pi minus plus 0, which is pi radians. Now, one time, look at the domain. The domain does not include pi as a solution. Yeah? Doesn't include pi as a solution. So one time, x cannot be pi. So we can say that how x is equal to pi is not in the domain. So we actually have no solutions for cosine x is equal to minus 1 for the given domain. Let's go in the second set of solutions. Over here, cosine is positive, so cosine is positive here and here. So my principal value is going to be cosine inverse the modulus of 2 plus root 20 over 8. 2 plus root 20 divided by 8 is that. Cos inverse of that, remember your calculator had to be in radians, 0.628. So x is equal, principal value, 0.628. In the end, we'll put to how much decimal places. X is the principal value in quadrant 1, which is equal to 0.628. And x is 2 pi minus the principal value, which is 2 pi minus 0.628. 2 pi minus 0.628. 5.655. Now, is this in the domain? Let's check and see. Remember, pi radians is 3.14. Yeah?
Yep.
This is more than 3.14. Yeah? So we say when x is equal to 5.655, this is not in the domain. So for this piece of the solution, x is equal to 0.628, the 3 decimal places. And as I rinse and repeat for the last quadrant, I'll move this around. For the last set of quadrants here, let me check and see. The principal value is cosine inverse of 2 minus root 20 over 8. This will be a negative. So again, solutions are going to lie here and here. 2 take away root 20 divided by 8 is that. So cosine is negative. Cosine is negative in those two quadrants. Multiply that by -1 to get the positive answer. And cos inverse of that is 1.257. X is equal to pi minus 1.257. Pi minus 1.257. 1.885 and pi plus 1.257. We can simply say this one is not in the domain one time because it's pi plus something. Nice. So therefore, for this set of solutions, x is equal to 1.885 to 3 decimal places. And generally, my solution, x is equal to 0.628 and 1.885 radians. Let's put radians. 1.885. You don't have to put radians, but I will recommend it. And both of them are to 3 decimal places. So this was a pretty intense question, right? This is probably as hard as you will get. You'll never get this for CSEC, ever. But it's good practice. Anything that precedes this should be a lot easier, and we will be exposed to a lot easier questions. Yeah?